Electronics are everywhere, as you know, in your telephone, in your MP3 player, and of course in the internet. The thing about the internet, the backbone of it, is of course the connections between computers everywhere. But what a lot of people don't realize is how much storage space is necessary to run the internet. For example, if you were to look at what assets Google has, they have warehouses full of hard disk drives to store vast amounts of information. This is a hard disk. It's from 1985. That's what the inside looks like. The way it works is the disk spins and the information is stored as little magnetic elements on the surface of the disk and is read by a little spindle that moves back and forth along the radius. In 1985, this cost £1,500 at a time when the computer that it was attached to cost £1,000. So it was a significant thing to buy. It stored 20 megabytes, which is about enough to store 5 songs from an MP3 format. Today, you can get discs like this fairly cheaply. This is from an iPod. It stores 4 gigabytes worth of storage and lots of songs. I don't know how many. So something interesting has happened between 85 and today that allowed us to have hard disks that are cheap and can store vast amounts of information. You would not have Facebook, Google, YouTube, any of those things without this revolution. The interesting question is, what happened to make this possible? The story begins not with the surface of the disk, but how we read the disk, not even how the information is written. In 1985, the thing that read the information was a coil of wire. The coil generated a current as it passed by the moving magnets through Faraday's induction law, something that you learned as a child in school. If the magnet moves or the coil moves, it generates a current. Problem with that is that the coil sensitivity depends on its area. So if you want to increase this from 20 megabytes to say 40 megabytes, you have to make the storage elements smaller for the same size of the disk. And then what are you going to do about the coil? If you make the coil smaller, the sensitivity goes down. If you keep the coil the same size, then you start to read several magnetic bits and you don't have any information. So the revolution that happened was getting rid of the coil and replacing it with something different. And that thing that's different is called a resistor. Something you're very familiar with, but it's not an ordinary resistor, it's a special resistor. And that's where the story begins. In 1988, there were groups of physicists working in France and another group in Germany. And they were interested in materials that don't occur in nature. These materials are layered. They're structured so that you can grow a material like cobalt or iron, and then a different material like copper, chromium, which is not magnetic. Cobalt and iron are magnetic, and then repeat it and do it many, many times. What they were interested in is, will the magnets interact with each other? What will happen if we pass a current through these structures? So fundamental physics about what we now call nanomagnetism. The reason we call them nano is because the thicknesses of these layers are measured in nanometers. In fact, a typical structure has a thickness of about 3 atoms. So very specialized techniques are required to grow these layers and not have them mix one with the other. And that's part of the reason why it took so long to develop machines which were able to produce layers like this that didn't mix. So they were studying these things, and the group in France was very interested in passing currents through these things and measuring what happens. What they discovered was that if you apply a magnetic field, the resistance of the structure decreased by a huge amount. So in looking at how this effect came about, they realized that given a certain amount of copper or chromium between the magnetic layers, then the magnets would interact to either align themselves parallel throughout the stack or anti-parallel, like in the diagram. When you apply the magnetic field, all the magnets will line up in the direction of the field. So what they quickly realized was that this is something to do with the interaction between the electrons and the individual magnetic layers. When they're anti-parallel, the resistance is high, and when they become parallel, the resistance is low. Now, compared to measuring the resistance of an ordinary single piece of cobalt, a magnet, this resistance was much, much higher. So they called it giant magnetoresistance. And as time passed, the effect became so important to both society and physics that it won the Nobel Prize in 2007. So that's the phrase that you might have heard, giant magnetoresistance, or it's abbreviated to GMR. And that's what it is. But how does it work? The interesting thing is that one property that you're well familiar with of an electron is the charge. Another property is the spin, what we call spin, but it's really a magnetic property. So you can think of spin up and spin down as like north and south. So the effect relies on the interaction between the electrons that pass through the layers, making the electrical current, and how the layers themselves are arranged in the magnetic moment. So as you can see in the diagram, the big yellow stars refer to a strong interaction that makes resistance. If there's no star in the path, then the resistance is much lower. So what you can see when the magnets in the layers are anti-parallel to each other, then the spin-up one, which means it's parallel to one of the magnets, passes through easily. But when it gets to the other magnet, it's now oppositely aligned and it has a hard time getting through. The opposite is true for spin down. When it meets the left-aligned magnet, it has a hard time to get through, but then an easy time in the other thing. So when you add these two resistances in parallel, this makes a high resistance. Okay? When you look at the other one, you see that now one of the electrons is always anti-parallel to the magnet and has a hard time getting through all the magnetic layers, whereas the other one has an easy time getting through. So most of the current now, when you add them in parallel, is carried by the lower resistance path, and so the total resistance of the stack is much less. So this is why when you apply the magnetic field and switch the magnets round, the resistance goes down. This spin carries all the current. This is a quantum mechanical effect, and that's why physicists are interested in it. But those people who were discovering this physics at the time realized immediately that it would have serious implications for technology. And so patents were taken out. IBM, in less than 10 years, turned it into the sensor that reads the information from the hard disk. The way it works, it only relies on having two layers. One layer they fix, so it's always pointing in the same direction. The other layer moves, and it moves in response to the stored elements on the hard disk plate. So as the disk spins by, this moves back and forth to be either parallel or anti-parallel to the reference layer. That's called a spin valve. It's a valve because it's like open or closed. And then the resistance changes rapidly from up or down. So if you think back now to the old scaling problem with the coil, a resistor doesn't have the same problem. You can scale everything as you wish, make the resistor as small as you can fabricate it, and shrink your bit sizes on the disk plate as small as you can, and that's the first clue to how the revolution came about. And it's all thanks to quantum physics.